Welcome to Learning with Philemon. In the previous video, electrophilic addition, we looked at the mechanism of the reaction of alkenes with hydrogen halides and halogens. However, we only focused on the symmetrical alkene ethene. In the case of symmetrical alkenes, there is only one possible product. As seen in the diagram, when ethene reacts with hydrogen bromide, bromoethane is formed. It does not matter whether the hydrogen bonds to the first or the second carbon. The product is still bromoethane. As we will see in this video, when the alkene is unsymmetrical and the molecule that is added is unsymmetrical, there are two possible products. Propene is an unsymmetrical alkene. This can be seen by rotating the molecule by 180 degrees about this axis. The molecule would not look the same after the rotation due to the CH3 group. Hydrogen bromide is also an unsymmetrical molecule using this same logic. When propene is reacted with hydrogen bromide, there are two possible products. The major product, more of which is produced in the reaction, is 2-bromopropane. The minor product, less of which is produced in the reaction, is 1-bromopropane. For more on how these products are named, please watch the IUPAC naming video. Note that the difference between the two products is which carbon involved in the double bond bonds with a hydrogen atom and which bonds with a bromine atom. In the next slide, we will see the justification for this based on the reaction mechanism. In electrophilic addition, the electrons in the double bond are attracted to the slightly positively charged hydrogen atom. In the first pathway, this carbon bonds to the hydrogen atom, leaving a positive charge on this carbon. In the second pathway, this carbon bonds to the hydrogen atom, leaving a positive charge on this carbon. It turns out that this carbocation is more stable. This is because the shared electrons of these carbon-carbon bonds are attracted towards the positive carbon, as depicted by the green arrows. As the electrons are closer to the positive carbon atom, it has a slightly less positive charge. This effect is called hyperconjugation. The more alkyl groups a positive carbon is bonded to, the more stable the carbocation is. This carbon is only bonded to one other alkyl group. Hyperconjugation is not possible with hydrogen atoms. As a result, this carbon maintains its positive charge, making the carbocation less stable. Because in the first pathway, the carbocation is more stable, it is more likely to form. This is because the activation energy, the minimum energy required for this step in the reaction, is lower than in the second pathway. For more on the concept of activation energy, please watch the energetics playlist. Because this carbocation is more likely to form, so is this final product. This means that there will be a higher yield of the major product than of the minor product. A useful way to remember Markovnikov's rule is that to form the major product, the hydrogen of the hydrogen halide adds to the carbon that is bonded to the most hydrogen atoms. The reason for this is, of course, that if the carbon is bonded to more hydrogen atoms, it is bonded to less stabilizing alkyl groups. The halide ion then bonds to the second carbon that was involved previously in the double bond. Thank you for listening. To consolidate your learning, try to draw a few mechanisms by yourself. If you haven't already, please subscribe for more content. Stay curious.